In a separate video, we come up with an equation that we call the non-relativistic velocity addition formula, which explains how you combine one velocity with another when you're dealing with low speeds, speeds that are small compared to the speed of light. In this video, we're going to talk a little bit about the distinction between speed and velocity, which some of you may know and some of you may not. And we want to do some practice with velocity addition. Okay, so first a word on speed and velocity, right? So let's say that you are in Boston, or say at Wellesley, right? And you wanna travel up to, I don't know, where do we want to go? You want to go to Maine? No, go to New York. Let's say we go to New York. Okay, so somewhere down here is New York City, and I'm guessing here, but let's say they're 400 miles apart, and let's say you're driving 60 miles an hour, and you want to know how long it takes to get there. Okay, well, one thing you might do is you might say, okay, well, it's 400 miles away. I'm driving at 60 miles an hour, so if I know the distance and I know my speed, I can find my time. But nowhere in this situation did I tell you you were actually driving in the direction of New York City. Like, what if you were actually driving in the direction of Maine? Right? So somehow the speed alone doesn't tell you everything that you need to learn about where you're going to end up. So that's the main distinction between speed and velocity. Right? Velocity is speed plus direction. So examples of velocity would be 20 miles per hour to the right, or 50 miles per hour due north, or 16 meters per second at 13 degrees south of east. Right? I need both a speed and a direction. In contrast, speed is just the first part of velocity. So the 20 miles per hour, or the 50 miles per hour, or the 16 meters per second. So speed is the magnitude of a velocity. But there's no associated direction. The other item that we need to know is that for the purpose of this class, all of the motion that we're going to talk about is one-dimensional. So you're either going to be moving to the left or to the right, or not moving at all. So we could say you're moving 5 miles per hour to the left or 5 miles per hour to the right. But physicists are lazy people, and they don't like to write to the left or to the right because it takes too long to do that. So we just need a way to keep track of to the left and to the right. We need a symbol, so we use a plus or minus symbol, and our symbol would be, if you're going to the right, it's a positive velocity, and if you're moving to the left, it's a negative velocity. And as we've already done, we often won't write +5, we'll just write 5. So it's either minus 5 miles per hour, or we'll just typically write 5 miles per hour for a velocity to the right. Now notice that both v1 and v2, these two velocities, have the same magnitude, right? So the magnitude of v1, or its absolute value, is going to be the absolute value of minus 5 miles per hour, which is 5 miles per hour, right? Absolute value here just means get rid of the sign and keep the magnitude. The same is true for v2. The magnitude of plus 5 miles per hour is just 5 miles per hour because it's already positive. You don't have to do anything to it. So what we see is that v1 and v2 have the same magnitudes. In other words, they have the same speed, but they have different velocities. One's moving to the left and one's moving to the right. So the next thing we want to talk about, and we're pretty much almost done with what we need to develop here, is we want to come back to the velocity addition formula that we developed in the previous video. And in that case, we saw like the velocity of a ball relative to the ground was equal to the velocity of the ball relative to the train plus the velocity of the train relative to the ground. And we said that, it doesn't have to be a ball and a train, it could be anything. So we extended that to just use x, y, and z. And we said the velocity of object x relative to reference frame z is the velocity of object x relative to some other reference frame y plus the velocity of y relative to z. And that equation that I boxed up is what we call the velocity addition formula that's valid at non-relativistic speeds. Well, what does that mean? That just means speeds that are small compared to c. What's c? Well, c is a symbol that we use for the speed of light. So this equation works as long as all of the velocities in the problem are small compared to the speed of light. Okay, that's fine. One thing we can do here, though, is formally show that the velocity of a relative to b is equal to minus the velocity of b relative to a. So we're going to show, we'll show that the velocity of x relative to y is equal to minus the velocity of y relative to x. And to do this, let's just draw a picture first to get a specific example. Imagine we have a ground, the earth, and we have a house attached to the ground, so that house is not moving, and we have Bob standing still also on the ground. So we have a house, and we have Bob, and then we have Alice in a car, and Alice is driving to the right relative to the ground. Okay, so this is Alice. Now, in order to match the nomenclature or the XYZ, what we can do is just relabel Alice and the house and Bob. So we'll call the house X, we'll call the house X, and we'll call Bob Z, and we'll call Alice Y. Okay? And then we come back to our equation, Vxz equals Vxy plus Vyz, and we notice right away that since Bob and the house are at rest relative to each other, that means that we know Vxz is equal to 0. Okay, so we have 0 equals Vxy plus Vyz, but remember the reference frame z is the same as the ground frame, which is also the same as the house frame. So we're allowed to swap out the reference frame z for the reference frame x because they are the same reference frame. So the velocity of the car relative to Bob is the same as the velocity of the car relative to the house. Okay, and that's basically the final step. We have Vyx equals minus Vxy. So I call this reciprocity. Okay, if you swap indices, you swap the sign. Okay, the velocity of a relative to b is minus the velocity of b relative to a. And this, it turns out, is true at low speeds or at high speeds. This is true at any speed. So we'll close out this video by doing a little bit of practice using velocity addition. Just as a reminder, we had the case, I'll just put up the equation. Vxz is Vxy plus Vyz. That's our non-relativistic velocity addition. And we had already done the case where Alice was throwing a ball on a train, and the ball was moving and the train was moving, and we wanted to know the ball speed relative to the ground, or Bob on the ground. And we found that if the ball was thrown to the right and the train was moving to the right, then we would add those two together to find the speed on the ground. But in general, we want to know what to do, like what happens if we're not throwing the ball in the same direction that the train is moving. So the example that we'll do here is a slight variation on the previous example. So the scenario is the following. We have Alice on a train. The train is moving to the right relative to the ground. We have Bob standing on the ground, and he's at rest relative to the ground. And as always, Alice is able to throw the ball at 3 miles per hour. But this time, instead of throwing the ball towards the front of the train, she throws the ball towards the back of the train. And the question we have is, what is the speed of the ball relative to the ground? So the quantity we want to know is v little b for ball relative to the ground. That's what we want to know, okay? And we know that we're going to find it by velocity addition. And recall that we take the two indices of the thing we want to know, and those become the outer indices of our equation. So we have VB relative to something plus V of that something relative to the ground. Okay, and then we can like look back at our picture and say, okay, well, what information do we have? Well, we know VBT and we know VTG. So if we put T in here, then we will know both of those terms. So let's do that. So I'm going to put T in here. So I can then proceed if I know the velocity of the ball relative to the train and the velocity of the train relative to the ground. When I add those together, I will get the velocity of the ball relative to the ground, and I'll be done. Okay, well, the good news is I have all of these. If you recall, we know that the ball can be thrown at 3 miles per hour relative to the train, and in this case, it's being thrown towards the back of the train. So VBT is not 3 miles per hour, but rather minus 3 miles per hour because it's being thrown to the left. And sticking with the numbers that we've used before, the train is moving to the right relative to the ground, and let's just keep the same numbers we've used in the past of 21 miles per hour to the right. So now when we incorporate all of this information, we have ball relative to train is minus 3 miles per hour, and train relative to ground is plus 21 miles per hour. So we add those two together, but one of the terms is negative. So we really have 21 minus 3, or 18 miles per hour, okay? And so we can see in this example, the velocity of the ball thrown by Alice and the velocity of the train are not actually reinforcing each other, but they're actually serving to cancel each other out. So this brings up an interesting point, right? It looks then that if I were to throw the ball harder and harder to increase the speed of the ball above 3, I could eventually, in principle, get it to match the speed of the train. And if I did that, then I would have 21 miles per hour of the train minus 21 miles per hour of the ball relative to the train. When I added those two together, I would get 0. So let's play that out. Let's say case 2, Alice can throw the ball faster. And we can be more quantitative than that. We can say the V ball relative to the train can be 21 miles per hour. And let's say she throws it to the left. And if the train is moving at the same speed it was before, we have VTG of plus the same speed of 21 miles per hour. And so then we say, well, what does Bob see, right? What does Bob see or measure for the speed of the ball? Okay, well, that is equivalent to saying what is VB relative to the ground, the velocity of the ball relative to the ground. Well, just like before, it's ball relative to train plus train relative to ground, and that we just said was minus 21 miles per hour plus 21 miles per hour, which is 0. So that suggests that the ball is not moving relative to ground. And that's a tricky thing to envision, right? It's rare that you see something shot out or thrown, but relative to you, it's not moving at all. There's a wonderful Mythbusters episode where they actually do this. They have an air cannon, they shoot a soccer ball out the back of a truck that's moving in one direction, and they shoot the ball in the other direction, such that relative to the ground, that ball is stationary. It comes out of the truck, and then it just kind of falls straight to the ground. Doesn't move left, doesn't move right. There are other examples of this, though, that you may be more familiar with, right? Like my kids love to go on moving sidewalks, and then run in the direction opposite that the moving sidewalk goes. So when I stand on the ground next to the moving sidewalk, it looks like they're not moving relative to me. We're just looking at each other in the eyes. They're not drifting left. They're not running right. They're just staying in place relative to the stationary ground. But of course, they are running their tails off, trying to match the speed of the moving carpet.